Okay, this section is on self-adjoint matrices. And for self-adjoint matrices, the spectrum or the eigenvalues, eigenvectors have very special properties. Okay, so we say, remember that a matrix A is self-adjoint if A is equal to AH, or A. We also say that this is equivalent to A being Hermitian. So this is also Hermitian. Okay, so in the case when A is Hermitian or self-adjoint, first thing we can say, even though the matrix is complex, if it's Hermitian, then the eigenvalues are real. Okay, so so that's quite a statement that the in this case, the eigenvalues have to be real. So this is also true, for example, for a symmetric matrix. If A is real and symmetric, then the eigenvalues also have to be real. Okay, so what's the proof? So let lambda x be a right eigenpair. That means that ax equals lambda x. And if I were to take the Hermitian of each side, I would get x Hermitian, a Hermitian is equal to, now when I take the Hermitian here, I'll get x Hermitian, and I take the Hermitian of a scalar, so it's complex conjugate transpose, so that just gives me a complex conjugate on lambda. Okay, so now we know that A is Hermitian, so AH has to be, I guess if we go back here and multiply by xh on the left, so that'll give us xha xh, and then multiplying on the left here we'll get lambda xh times x, and now I know that A is Hermitian, so I can replace, and let's see, what is my logical jump here? Okay, so I multiplied, yeah, maybe I should fix this. I took this guy, multiplied on the left by xh, and then I took this guy and multiplied on the right by x. So this one gives me this expression, and this thing gives me this expression. Xh AHX equals lambda bar times xh. And then we know that A is Hermitian. So A Hermitian is equal to A. So this guy has to equal that guy. That means this has to equal that, which means that lambda and lambda bar have to equal each other. So if the complex conjugate, if you have a complex number and it's equal to its conjugate, complex conjugate, that means it has to be real. Okay, so that gives me the real. I think I'll rewrite. I'm gonna rewrite this, and so look for the updated notes. Okay, but the main thing is that if A is Hermitian or self-adjoint, then the eigenvalues are real. Well, what about the eigenvectors? So turns out the eigenvectors have a lot of structure as well, but let's just start with a case that's easy to prove. Okay, so if A is Hermitian, and let's suppose that the eigenvalues are distinct, so geometric multiplicity equals algebraic multiplicity, then in that case the eigenvectors are orthogonal. In fact, the eigenvectors will be orthogonal in general, even if the eigenvalues are not distinct. So let's prove it when they're for the case when they're distinct. So let lambda 1 x1 and lambda 2 x2 be distinct eigenpairs. That means that lambda 1 is not equal to lambda 2. And we know that, first of all, we know that a x1 is equal to lambda 1 x1, and then let's multiply on the left by x2. So x2h a x1 is equal to lambda 1 x2h x1. And we also know that, I've skipped a little bit here. We also know that x2 is equal to lambda 2 x2. So let's Hermitian. If we Hermitian both sides, so we take the Hermitian of both sides, we'll have x2h, ah is equal to lambda 2. We know lambda 2 is real, x2h. And then if I multiply on the right by x1, I get this expression. So we know that x2h x1 is equal to lambda 2 x2h x1. And we know that a is Hermitian. So this thing is equal to a. So these two sides are equal. That means these two sides have to be equal. So if I pull the x2h x1 like that, then I've got lambda 1 minus lambda 2. So in other words, I took this guy, subtracted that guy, and I get this expression. Now, we know that these are distinct. So lambda 1 and lambda 2 are not equal to each other. So because they're not equal to each other, we have to have that x2h x1 is equal to 0. And that means that x1 and x2 are orthogonal. So, yeah, if A is Hermitian and the eigenvalues are distinct, we've shown that they're orthogonal. And we can always, because an eigenvalue vector really defines a space, we can always pick that vector to be orthogonal or to be unit length. So it's orthonormal. Okay, so it turns out that there's a nice theorem, the spectral theorem. This theorem's not easy to solve or to prove, but it's true that if A is Hermitian, then the algebraic multiplicity equals the geometric multiplicity for every single eigenvalue. So it turns out then that we can basically extend our previous proof from the case where they're distinct to the general case. So the corollary is that if A is equal to AH, so if A is Hermitian, then there's a unitary matrix U and a diagonal lambda, so that A is equal to U lambda UH. In fact, this is, we can say even more, an orthogonal. This is an orthogonal matrix U and a real diagonal lambda, so that A is equal to U lambda UH. Okay, so if it's Hermitian, then we can diagonalize A, and the eigenvalues are real. We can diagonalize, and we can always pick the eigenvectors to be orthonormal. So in other words, U is an orthogonal matrix. So this is a pretty, let's see. Let me make sure. It's orthogonal. Actually, so actually unitary is correct. So if A is complex, then U will be unitary. If A is real, so if A is real, then U is orthogonal. So yeah, if I have, for example, a real symmetric matrix, then the eigenvectors are going to be, I can always choose the eigenvectors to be orthonormal. They're always going to be orthogonal. I can choose them to be orthonormal. The eigenvalues will be real. Okay, so this is an important property that we use for symmetric or Hermitian matrices. Another thing we can say is Okay, so if A is yeah, I guess I would probably put this on a different slide. We're not requiring that A is Hermitian here. We say if A is a square matrix and it loses rank, so the rank is R, which is less than the dimension, then at least m minus r of the eigenvalues are equal to 0. So when a matrix loses rank, some of its eigenvalues become equal to 0. Okay, so that's all I had on self. This actually is true whether it's Hermitian or not. But the main takeaway is if a matrix is Hermitian, then its eigenvalues are real. Its eigenvectors can be chosen to be orthonormal. If A is symmetric, then in fact its eigenvectors can be chosen to be, or U can be chosen to be an orthogonal matrix.